All right, so I think we're in week 6, by the way, which means that we are on our way. So Victor, you just said that's the only thing you hear? Can you not hear me talking? Oh, he just said no. Huh. Can everyone else hear me?
Yeah.
All right, so Victor, I think it's on your end. Oh, now he hears. Okay, good. Anyway, so well, I think we're in week 6, which means we're halfway there. Yes. At least halfway through this quarter. We'll see what next year has to bring for everybody. But so last time we talked about simple harmonic motion, and we saw a bunch of different examples. We talked about pendulums and springs and things rotating. But what was what defines something as simple harmonic motion? Do you guys remember what the one characteristic they all had in common was? So Victor just put in the chat, it was like the equation structure. I think maybe you could say that like they all ended up getting the same kind of equation, and it was a cosine or a sine, which Ralph then kind of put there, waves. We did see that if we wanted to graph the motion, at least absent of things like losing friction and all that, that it did end up being sinusoidal. But I'm going at something even deeper, like what even led to the fact that all their equations ended up being sines or cosines. How about this? This might help Ian. We got solutions that were sines and cosines from a differential equation.
Yeah.
What kind of differential equation gives us sine and cosine as solutions?
I mean, second order.
Okay.
But it's also when the R is of imaginary value.
Okay. So what would it have to look like for it to be second order and imaginary? So think about second order means a second derivative. What's the second derivative of position?
Second derivative of acceleration.
Okay, so it's acceleration. And then in order to ensure that we got real solutions to the polynomial, and I know I'm talking over everybody else's head, but to get real solutions, that acceleration has to equal a negative of the original of the position.
Yeah.
So for simple harmonic motion, the definition, we get simple harmonic motion when the acceleration is proportional to the position.
Yeah.
And points in the opposite direction. So that's really the key. So this is now everybody back on that, right? That's what's important for simple harmonic motion. If you're ever in a scenario where your acceleration is proportional to your position, but pointing in the opposite direction, you will get simple harmonic motion. And that's why we saw it with springs. That's why we saw it with pendulums. That's why we saw it going in a circle, is we always have that relationship. Okay, so.
That's every time, correct?
When you say that's every time, you mean for every simple harmonic motion? Yes.
Yeah, the acceleration will be negative and proportional to the position.
Yep, so A is going to equal negative kx.
Yeah.
Yep. So as long as that's what we've got, whatever's causing it, that will end up giving us simple harmonic motion. Basically, it just means you're going to be oscillating back and forth, right? Simple harmonic motion it really comes down to there's a back and forth between two positions happening in a regular way where you get maximum velocity in the middle and maximum acceleration at the ends, right? So, so anything that we can classify that way will be simple harmonic motion. Okay, so what does this have to do with waves? Like, why do we talk about it beforehand and all that? It should be pretty clear because of the fact that the formulas gave us sines and cosines. And so really naturally leads us to wave motion, because imagine you've got a buoy that's just floating out on the ocean, right? Or a boat or whatever that's just floating on the ocean. As the waves come by, think about the motion of that boat. It's going to go up as the wave comes by, then it's going to drop. Then it's going to go back up, and then it's going to go back down. And you notice that that is going to be simple harmonic motion. So there's another example of where we can get this. So that's why waves comes naturally after simple harmonic motion, just because of the fact that they are kind of integrally linked. Okay, so let's talk waves. Now, the first thing that we have to consider is that waves are actually going to be functions of two variables. And I know most of you don't really know how to deal with that. Although maybe, have you guys hit multivariable?
That's what we're doing right now.
Okay, so you're just getting to that. So you're just starting to see how that works. But waves are actually going to be functions of two things. They're going to be functions of position and they're functions of time. Okay, so we're going to have to construct an equation for them in terms of the both. Luckily, we're going to usually look at one or the other. We're going to make it either what we call time independent or position independent. And we'll talk about the difference there. But this is going to make things a little bit more complicated than just a regular old sine wave. I mean, it is a sine wave, but there are going to be multiple things that are affecting it. And so when we start talking about things like periods, wavelengths, and all that, we're actually going to have to think about wavelengths in time versus wavelengths in distance, or frequencies in time versus distance, and the like. So let me go to the whiteboard, and let's just start with developing what the equation needs to look like, so that it depends on both time and position and kind of what all the different pieces are. Okay, so let's go to the board. So here's what we're going to do. We're going to start by creating the wave kind of like we're used to. And I'm going to use cosine, even though sine is perfectly fine as well. You guys know I like cosine a little bit better, and I think it works a little bit easier with things. But we're going to have an a cosine. Now, in here, you may remember an omega t. Well, that's going to be part of this, because there's also going to be a kx. And so these are the two pieces that allow for changes in position, or with changes in position, and with time. Okay, so we're going to have a kx. We're also going to have an omega t. Now, to finish this off, we're going to put a minus sign. So we've got kx of minus omega t. But that minus can be a plus. It doesn't really matter. Okay, so what we want is something of this form. And I am going to put on a little plus phi, because that will allow any kind of a phase shift as we go. Okay, so let me explain where these different things are going to be coming from and how they're related. So let's just start with a graph of a cosine. And let's say that this is what we see at time 0. All right, so imagine we just took a picture, and this was at time 0, right? We take a picture of the wave, and this is what it looks like. Okay, so if time is equal to 0, this little time piece goes away. And you notice that we now would just have a cosine of kx. There isn't going to be a phi, because I've got this thing set up so it's got a max at time 0. But obviously, if it was slid over left or right, we'd have to deal with that phi. All right, well, in this picture, let's just kind of put some of the important things down here. In terms of locations on the x-axis, there's going to be pi over 2, that's pi, 3 pi over 2, and 2 pi. So we're going to do things here in radians. And in terms of how far it's going to go up and down, its maximum is going to be a, and then the minimum is going to be negative a. So you already know about that. A is the amplitude, and that's still going to be there. Okay, but I want to talk about K. How do we figure out what K is? Well, K has to do with the period, but in this situation, excuse me, in this situation, our period is actually what we call the wavelength. So when we've called it the period before, like in a trig class or a calculus class, period was how long it takes to repeat. But in the physics world, we use wavelength to talk about the distance needed to repeat. So that's how far away you have to go to get to being on the same part of the wave. All right, so we call that the wavelength. The letter that we use for wavelength is the lowercase lambda. You haven't seen that before. That guy's lowercase lambda. And so that's going to be wavelength. So this K, that's going to depend on lambda. You may remember the formula for this is that this thing was 2 pi over the period. Well, again, it's not the period, but it's going to be K over that, or 2 pi over that. So K is going to equal 2 pi over lambda. And so this number K, excuse me, we call this the wave number. So every wave has a wave number. It's 2 pi divided by the wavelength.
Just in this specific example with the graph you have, it'd be 1, correct?
Yes.
Okay, just making sure.
Yep. So, excuse me. I should probably be more generic with these things, right? But yeah, it would be whatever the length is. So in this case, 2 pi. So this one would have a wave number of 1. All right. So at any moment in time, we take the picture, we can measure that wavelength, get the wave number. And we could also get a phi if we weren't perfectly in phase. I apologize. I got a total frog in my throat. Hold on. I think all these hours of talking on the computer are starting to catch up on me. All right. So that's where that K is going to come from. It's going to be 2 pi over lambda. Now, let's think about this wave. This wave can actually move. Because let's think about like an ocean wave or something. if we were to take a picture of the wave on the ocean, and then a little bit later take another picture, it would appear as if the wave moved, as if this max worked its way over to some point over here. And so there is going to be a speed for the wave. So let's say that this wave is moving at some velocity v. So if it's moving at a velocity of v, we know that it's going to move a certain distance if we multiply that by t. Right? So if we've got a velocity of v, then it's going to move a distance of v times t. Well, that's a horizontal shift. So if we're moving to the right, excuse me, how do we deal with a horizontal shift?
Subtract a phi.
Yeah, we're going to subtract. So, oh, and Ralph, frog on my throat, frog in my throat. Have you never heard that? When your voice gets kind of crackly, whatever. I guess it's really old-timey because I'm an ancient old man. I use weird phrases like that. So, excuse me, frog in my throat. There you go. You learn something new every day, right? Okay, so let's do a horizontal shift by subtracting. Well, where we are so far, we'll come back to this in a second, but we currently have a times the cosine of 2 pi over lambda times x, right? That was our, we just took a snapshot, and that's what we see. But now if we let it move, that's going to change this, 2 pi over lambda times x minus vt. So that's that distance vt that we're moving to the right. All right, so we can distribute that. Take that 2 pi over lambda and distribute it through. So we get a times the cosine of 2 pi over lambda times x minus 2 pi over lambda times vt. And you're starting to see how this is looking like the kx minus omega t. Right? So we've got our k is the 2 pi over lambda, but now omega is going to be 2 pi v over lambda. All right, but let's go back to what we know about omega, right? Omega, that's actually 2 pi over the period. So let's rewrite this as 2 pi over the period equals 2 pi v over lambda and so what this is suggesting is that the period is equal to lambda over v. And if you look at that, that makes total sense. So think about what lambda was. Lambda's wavelength, so that's how far we have to go from like peak to peak. The velocity is how fast we're going. So if you were to take distance and divide by velocity, so good old dirt formula, you get time. So that's why we actually can call this omega, because it is doing exactly what omega did before. It is related to the period. The period now, though, depends on your speed. Okay, so important things again. We've got the wave number. We've got, this is a way of calculating our period. But even better, here's what's kind of nice, this omega stuff, is that the relationship between omega and k is totally dependent upon that v, because that v is equal to lambda over t. Okay, well, t, that was 2 pi over omega. Lambda, that's equal to 2 pi over k. And so if we invert and multiply, we have this relationship between v, omega, and k. So if you ever want to know how fast a wave is moving, if you know the wave number and this number omega, right, which is the angular frequency, but if you know the wave number and the angular frequency, you'll know how fast it travels. So then that plus phi, that's really just used if we need it. But other than that, it's kind of the big piece to how waves behave mathematically. But I do want to show you another form, and this one involves frequency. Okay, so I'm going to keep this one up top. So let's remember this guy. But what if instead of other quantities, you know the frequency? All right, well, what do you know about frequency? What do you remember about frequency?
The amount of repeats that something has in a given time frame.
Okay, so it's how many times it comes by in a certain chunk of time. Yep, that's a good way of thinking about it. Do you remember how it's related to period?
Isn't it like the inverse of period, or?
Okay, it is. It's the reciprocal. So we just flip it over. So frequency is actually 1 over the period. So we got that. Which means everywhere that we had the big T, we can replace it with frequencies. So think about like omega. Omega was 2 pi over T, which means it's the same as 2 pi times F. Which means if we don't want to have omega up there, but we'd rather have it in terms of the frequency, not angular frequency, we could write this as y equals a cosine kx minus 2 pi f times t. So we could write it like that. We could also, if we were to take that k and replace it with the 2 pi over lambda, no, so what we can do is pull out that 2 pi multiple. So we get a times the cosine of 2 pi over lambda x minus 2 pi ft. So I can pull out that 2 pi and get cosine of 2 pi times x over lambda minus f times t. And now this is in terms of only like linear quantities as opposed to angular quantities. So let's go ahead and put a box around that one. because this one's kind of useful too. But notice that now, instead of knowing a wave number and an angular frequency, instead we know a wavelength and a regular frequency, a time frequency. All right, so there's wave equations. That's what these things look like. And obviously, if we were to be moving the other direction, the only thing that would change is instead of a minus, it would be a plus. All right, so let's do this. Let's do an applied example just so we can kind of see how this works. So let's say that we're playing with a clothesline. So we just got a big string that's out, and we're just going to be playing around with it. And what we're going to do is we're going to start a wave. We're just going to kind of fling it up and down. All right, so we're just wiggling one end, making it go up and down so that we're creating a sine wave. But let me give you some information. We're going to see if we can get an equation for it. So the first thing I'm going to tell you is that as we're oscillating this up and down, okay, so here's our clothesline. It's like fixed over here. And then this side's in our hand. That's a hand, by the way. And that's just moving up and down to create the wave. Okay. All right, so let's say that we get a frequency of 2 hertz. Do you remember what a hertz is? What are the units of hertz?
Cycles per second.
Yeah, it's per seconds. So it's seconds to the minus 1. Okay, so we have a frequency of 2 hertz. Let me give you an amplitude of 0.075 meters. So we're moving it up and down 7.5 meters. And I'll even tell you the velocity of the wave. The velocity of the wave is 12 meters per second. So that's not the velocity of a particle on the string. That's the velocity of the wave. So I want to make sure that we have a good distinction there, understand the distinction. Because a particle on that clothesline is going to be moving up and down, right? Like if we had a safety pin on that clothesline, we would see it go up and we would see it go down over time. That's not the velocity I'm talking about. Velocity I'm talking about is if we were to watch this max, how quickly is that max moving along the line? So are we all good with the difference between wave speed and particle speed?
Is that 1.2 or 12?
12.
Okay.
Okay, so let's see if we can calculate wave number, angular frequency, all that good stuff, and then also get an equation for this wave. So this is our ultimate goal, is I want to write this as y equals a cosine of kx minus omega t. So let's start easy. Let's get the a. What's a? He says as he already had it written down.
0.075.
Is that 0.075? Yeah, that's the amplitude, how far we're going up and down. Okay, so this obviously is going to go in for our A. All right, what about K?
We don't know yet, but we can find out because we have frequency.
Okay, we got frequency. That in itself isn't enough to find K. It's enough to find omega.
That's what I was thinking, and then we could do V equals omega over K.
Okay, let's get omega. So we do know that omega is equal to 2 pi times f. So that's going to be 4 pi. So that is going to go in here. So Bradley, what did you say again by finding lambda?
Yeah, it's k equals velocity over omega.
It's actually
Or other way around.
It's
Other way
omega
around,
over v.
yeah.
Yeah, Cesar got that. He put that in the chat. That's right. So we are instead going to do the omega over v. So k is going to be 4 pi over 12, which is pi over 3. So here is the equation for that wave. It's going to be 0.075 cosine of pi over 3x minus 4 pi times t. All right, so it's actually not that hard to figure this out with this information, because frequency will always get you omega, but you're going to need something like v or lambda, some sort of a distance feature, in order to finish this out. Okay, so when we go and we use these, and a lot of times what we're going to do is we're going to look at things that are either time independent or position independent. And that really just comes down to which of these pieces are we involving. Okay, because like let's say that we take a picture, meaning we set our time. If we were to set our time, let's come back to this generic. If time is fixed, so we say we're taking a picture at time equals 2 seconds or 10 seconds or whatever. This part, the omega t, is now constant. And all that's going to do is give us some sort of a phase shift for our graph. And so if we want one that's time independent, actually, let me write it up top because I'm running out of space. So the time independent form looks like y equals a cosine of kx. There's also a position independent, which would be, okay, let's specify where we are in space. So this would be the, okay, I'm sitting here in the ocean. What happens to me as time goes on? Now you already know, like if this is the spot in the ocean, as time goes on, we're going to see that person go up and down, right? If you're floating out there. So you're still going to follow a sinusoidal path. It's just going to be dependent on time only. Well, it's the kind of same deal. Suppose that k is fixed, or sorry, x is fixed. Well, then the kx is constant, which again is just going to be some sort of a phase shift. And so for position independent, it's going to be a cosine of omega t. So in situations where we can do that, we're going to want to, because it's going to make the calculus a lot easier. Right, and you guys can see that. Because now if I wanted to look at how it's changing or something like that, then it's just going to be a simple derivative as opposed to a partial derivative. So Ralph just asked, why isn't it a negative? Anyone want to answer that question for him? Or maybe you guys don't know.
Can't you just pull it out and put it on the A?
If it was sine, I could.
Mm.
cosine's an even function, so negatives inside can go away. They basically just disappear.
That's the answer.
Yeah. And if it was sine, you might go, okay, well, what about that? Well, what that would do is cause a reflection, but a reflection is the same as a phase shift, so you could actually incorporate it into there. So really what I was doing, Ralph, is I was making use of my knowledge of the trig functions to allow myself to go, since all this stuff is generic anyway, that minus sign being there or not there in the term of cosine doesn't matter. And if it's sines, well, I can just pull it out and it'll get incorporated into A or make the phase shift change. It was hand waving. It was totally just making math shit up, and you guys all believed me. Okay, that was a joke. Although you wouldn't know the difference. Oh no, you've forgotten everything from trig. How dare you? Saying that kind of thing makes you dead to me, so watch out. All right. So now that we've kind of got an idea of how to describe this with an equation, let's see if we can calculate, say, velocities and accelerations and things like that. And specifically, I want to start with what's the velocity and acceleration of a particle that's in this medium. So like, let's say we're talking about the boat that's floating on the water as the waves come by. What's its velocity and acceleration as it's bobbing up and down? Okay, well, I'm not going to go to the time independent or position independent because I know you guys have now seen this math, at least maybe a little bit. Let's go back to this one that's both position and time dependent. So we've got a cosine of kx minus omega t. All right, now I want to find a velocity. And I want to find a velocity in terms of position. So what's happening if I've got a fixed position as time goes on? So if I want to find that velocity, so this is the velocity of the, I'm going to call it object OBJ, as opposed to the velocity of the wave. This is going to be a partial derivative with respect to time. I'm only concerned with what's happening as time progresses. So that's why it's going to be a partial with respect to time. All right, well, you guys should know, I hope, that when we differentiate with respect to time, we treat all other variables as a constant. So we're going to get the A out front. The derivative of cosine is a minus sine. So I'm going to get a minus A times the sine of kx minus omega t. Then I do the chain rule. And on the inside, I need to differentiate with respect to t. So the kx is constant, goes away. Minus omega t gives me a minus omega, which if I pull that out front, gives me an omega a times sine of kx minus omega t. So there's the velocity. You'll also notice that I didn't put a plus phi in here. A phase shift's not going to change anything, so at least in terms of what this looks like. But there's the velocity of this bobbing object as it's moving along with the wave. So we have omega a times the sine of kx minus omega t. Well, if we want to take the next step and get the acceleration of the object, that's going to be yet another derivative with respect to t. So it's a second derivative. Well, if I differentiate the same thing but with respect to t again, I'm going to get minus omega squared a times the cosine of kx minus omega t. And the minus omega squared, that came from the minus omega from the chain rule on the derivative. All right, so there is the velocity and the acceleration of just anything that's bobbing along. But notice a couple things. First of all, look at the velocity, or not the velocity, the position, and look at the acceleration. What's the difference in those two?
A negative omega squared.
Okay, so we're off by a factor of negative omega squared. So it is a scalar multiple of position. So your acceleration is proportional to position. And the negative just means but points in the opposite direction. All right, well, what is that?
Simple harmonic motion.
Here's your simple harmonic motion. This is why we know that a wave does the same thing. This is why we bring it up after simple harmonic motion, is that a physical wave is also going to follow simple harmonic motion, or at least a particle that's moving with respect to it. Bless you.
Thanks.
Okay, so that's kind of cool. That tells us that we're going to have greatest acceleration when we're at the top or the bottom of the wave. When you're at the top of the wave, you've got greatest acceleration going down. When you're at the bottom, you've got the greatest acceleration going up. Okay, so there's the first thing. I also want you to notice that we can figure out the maximum velocity and the maximum acceleration pretty easily just by looking at these equations. So a particle that's bobbing along on a wave or moving in a wave, what we're going to see here is the max velocity. So maximum, let's go speed. The maximum speed is going to equal omega a. Because look at this formula. If you look at the velocity, the sine bit we know bounces back and forth between plus and minus 1. So the biggest velocity is going to be omega times a. Does that look familiar?
Yeah.
Because we saw it not that long ago when we were talking about the spring and the mass and things bobbing around. We found that it was exactly the same thing in terms of its maximum velocity. And then if we look at maximum acceleration, well, it's going to be omega squared times a. So that omega, that angular frequency, does a lot in terms of the motion of particles that are in a wave. All right, well, I want to show you one more thing about this before we move on to different kinds of waves and all that. I want to show you the relationship between this acceleration in terms of position and your acceleration in terms of time. So I'm going to keep this bottom one because that was our second derivative with respect to time. I forgot to put the 2 here. Let's look at a second derivative with respect to position. So I'm going to want to do kind of the same thing, but this time let's do a d squared y dx squared. Okay, so let's see what's going to happen when we differentiate with respect to x. In terms of the cosine, it's going to turn into a sine, which then turns into a cosine. The a is still a constant multiple. But now when we do the chain rule, what are we going to get as our multiplier instead of the negative omega?
Negative k.
We're going to get a k. And so then, like Ralph said, he put k squared. By the time we do it twice, we're going to get a k squared. So the second derivative is going to be a minus k squared a times cosine of kx minus omega t. And that minus sign was the derivative of the sine. Right? Cosine goes to minus sine goes to minus cosine. Okay, so these two are very much related. And in fact, if you were to divide one by the other, notice that the cosine bit goes away, the a goes away, the minus signs even go away. And all we're left with is a k squared and an omega squared. All right, so check this out. So we'll take the first one we did, the one that changed with time. We'll divide it by the one that changes with position. And what we're going to get is omega squared over k squared. And I don't know if you recognize that, but just a little bit ago, we saw what omega over k was. Yeah, Victor just put that's v. So this is actually v squared. So you take the acceleration of the object in the position in terms of, time, and then you divide it by the acceleration in terms of x, and you get v squared. So we actually call this the linear wave equation because it relates how waves move versus how they move objects, right? The ddt was how it moved the object, and the ddx is how the wave itself is moving. So let me go ahead and just kind of put this back together. What we see is that the second partial with respect to x is equal to 1 over v squared times the second partial with respect to t. And I am going to box that. And this is called the linear wave equation. But it is kind of interesting about how nice and neat it is that these two things are only off by a scalar multiple, a constant multiple, and it's 1 over v squared. So I know I just threw a lot of math at you, but this is the relationship that we get when we're talking about waves. And you can see how when we allow for both time and position changes, it gets a little bit more gnarly, but you're to the point now where you've got the math and you can do it. All right, this is a good place to take a break. So let's take 10. Let's come back at 4:10 and we will keep chatting. So I'm going to pause. Okay, so now that we've done the math of waves, let's talk about different kinds of waves and where they show up, and then we'll start kind of tying it all together. So waves, there are two primary types of waves. They're what we call longitudinal waves and transverse waves, okay? And they both, or the way that we know the difference between them is what they do in terms of the motion on a particle within the wave. So think about the ocean waves we've been talking about. If you're just sitting out there on a boat as the wave comes by, you're going to move up and down as that wave comes by you. So the motion there is opposite or perpendicular to the direction of the wave travel. The other thing that could happen is we could have a wave that would take a particle and move it back and forth as that wave came through, so that that motion is in the same direction as the motion of the wave, or the traveling of the wave. So that's how we actually classify the two, is which way are they moving their particles. So let me go to the whiteboard just so I can write up the names. Okay, so again, it all comes down to which direction are we moving relative to the wave. All right, so the names of these are transverse and longitudinal. So transverse, this is the one where the motion is perpendicular to the wave's path or wave's travel. And so this is the ocean wave. So what we're going to have is our particle is going to say go up and down as that wave moves, say, to the right. All right, so that's transverse. So longitudinal, this is where the motion is parallel to the wave's travel. And so now if our wave is going, say, to the right, our particle is going to oscillate back and forth, left and right. So this is just how we classify them. In terms of examples of each, obviously the ocean wave is a good example of a transverse wave, as we see that boat bobbing up and down. Light also is a transverse wave. Examples of longitudinal waves are sound waves. So sound waves go back and forth. And some waves from earthquakes are longitudinal, but also some are transverse. I don't know if you've ever experienced an earthquake, but sometimes you can feel both types.
We had one just a few weeks ago, didn't we?
Yeah, there was one. Oh my gosh, yeah, it wasn't that long ago. It was a couple of weeks ago. I remember it was in the morning because my family hadn't gotten up yet. And I remembered I thought there was like somebody was trying to get into my house, is what I thought.
It was kind of scary.
And then I realized, oh, it's just an earthquake. Right? Oh, just an earthquake. When I was a teenager, when I was in high school, I grew up near Seattle, and Seattle, there are quite a few earthquakes, not quite like the Bay Area, but still pretty significant. And I remember we were sitting in a circle on the floor, and I heard, I was like, Jesus, why is there a truck in this, like residential area? And the next thing you know, I saw my friends across the floor, like raise up, come back down. And then I felt myself raise up and come back down. And I experienced a transverse wave, right? I mean, I definitely experienced, because me as that particle, I moved up and down because the ground moves up and down. But you also get a lot of those that are the side to side with waves or with earthquakes. And again, I'm sure you've experienced it. But I can show you examples of both pretty easily using a Slinky. Now, I don't know how well this is going to work out, because normally we're in the classroom and we extend this really, really far. This is like a huge Slinky. I don't know if you can tell. It's like about 3 times as long as what a standard Slinky would be. but I'll see if I can still show you guys here both kinds. So if you want to see a transverse wave with a Slinky, it's actually really easy. All you got to do is shake one side up and down, right? So if you look at that wave, I'll stretch it out just a little bit. Hopefully you can see the verticalness. Like if you were to look at one piece, like look at the piece that's near my chin, right? Or where my nose is right there. You're going to see that go up and down as this wave goes by, right? So the wave comes by, this piece goes up, comes back down, and then back up. So let's see if I can make it do that again. Just watch the bit like right under my nose. You can even see it moving right there, right? It's bouncing up and down. So that's an example of a transverse. You just flip it up and down. But what's great about the Slinky is you can also see pretty well the longitudinal. Let's see, maybe a background on my shirt will help. But what I'm going to do is I'm just going to kind of pull this tight, and I'm going to let go a couple of these little coils at a time. All right, and see if you can see what happens with the wave. You notice a difference, hopefully. Let me do it again. Look at the bit that's right under my nose. Okay, and just watch what it does. You see how it's vibrating left and right instead of up and down? So that's a longitudinal wave. If we were to actually like put a little sticky note here or something, then just watch this one coil, you'd see that coil go back and forth like this with the longitudinal, as opposed to up and down like that with the transverse. Okay, so we just classify them in different ways because their motion is different. The particle's motion is different, although their accelerations are still the same. Okay, like when we went and we calculated the acceleration, I was really careful not to call it, say, vertical acceleration, because that's not always the case. Sometimes it's acceleration that's moving in the direction of travel, so it could even be horizontal. Anyway, so we've got these two kinds of waves, and so we're going to see examples of each a lot. And while they move differently, they still all follow simple harmonic motion. And they have the same general formulas. And we can still talk about wavelength, and we can still talk about period and all that sort of stuff. It's just not as obvious for these longitudinal ones. It's a little bit harder for us to think about that because we don't see the motion so well. But again, take that one particle that was bouncing back and forth. In terms of its amplitude, it's going to be how far did it go on each side, right? So if it starts here and came out to that point, there's your amplitude, right? Well, it's half that distance, I guess, right? But that's how we would calculate amplitude. Period would still be, let's time it from being out on this end, down and back. That would get us our frequency, and everything else follows. We just have to think about, we have to kind of just flip our thinking a bit so that we're watching in the direction of travel as opposed to perpendicularly to it. Okay, well, this is another one that when we get back together at some point, I'll really show you this well so you can see, because it's pretty impressive. You can actually see the waves travel really, really well when we're in a bigger space. Okay. Sorry about that, my earbud popped out. All right, so let's look at some specific kinds of waves on specific media. And I want to start with a wave on a string because that's probably the easiest model. You can visualize it really well. I mean, you can make it. All you got to do is take any kind of a string, tie it off somewhere, and just start wiggling the end, right? So let's look at that mathematically and see what characteristics of a string are going to affect the wave in terms of amplitude, wavelength, period, speed, right? All that good stuff that we just did mathematically. So let's go back to the board. All right, so I want to look at a little chunk of string and see what happens to it as it's moving on a wave. And we're going to go ahead and make this transverse. So it's going to be one of those that goes up and down. Or you can think we're just like creating a pulse, not a wave itself. We're just like plucking the string and we're watching it go. Okay, so some things that we're going to need to know about said string. So first of all, here's what the string would look like without a pulse. It's going to be under tension. All right, so some sort of a tension that is pulling on it, say in this direction. All right, so there's a tension on this string. You can also think of that tension as being over here because the tension force is throughout the string. Okay, so we've got a tension on it. Now, the other thing that we're going to be interested in is its mass density. So imagine we were to take a little chunk of this string, just kind of look at it. If we were to weigh it and then divide by its length, we're going to get the mass density, and we're going to use mu for this. If you haven't seen mu before, this is mu. It's the Greek equivalent of m. It's their lowercase. So it's going to be our mass density. So this is just going to be mass divided by length. So if you had a big piece of string, you could just take the entire one or the entire piece, weigh it, and then measure its length, and that would get you your mu. All right, but we need to know the mass density. It's going to be mass over length. All right, so why do we care about this? Well, let's actually pluck the string. Let's create a pulse, and let's use Newton, his good old second law, and see if we can figure out with a force diagram what your acceleration needs to be. All right, so here now is a pulse going. And so let's just look at a piece over here. So we're going to have a little tiny chunk. And I want to draw a force diagram for this piece of the string. All right, so what do we got there, Victor? Cool, thank you. All right, so we got gravity. All right, so there's going to be a force that's pulling down. That's gravity. Okay, what else are we going to have? All right, good. We've got tension. And so the force due to tension is going to be pointing in the direction of the string. So it's not actually going to be horizontal now because of the fact that we gave it a little bit of a flick. But we do know that there's going to be that tension. All right, so that's what we got going on there, right? And so when we put it all together, the net force here is going to be add those pieces. All right, now think about another piece over here. Let's say we're kind of on the far side. You could kind of think of it the same way as that there's going to be a tension force on this piece. Well, actually, you know, let's just do it all in here. There's also going to be a tension force this way. That's going parallel to that. But the thing is that we don't necessarily know that those angles are the same. So let's break it into a theta 1 and a theta 2. So Victor, you just gave me normal force. There actually isn't a normal force here. There's nothing trying to hold it up other than the tension. Okay, so let's look vertically. So vertically, we're going to get the tension force from the one, or the vertical component of the tension force coming to the left and the one going to the right. So I'm going to call those, say, F1 and F2. And so what we know is that in the vertical, so we'll call this Y, we're going to have F1 plus F2. So those are going to be those guys, plus our gravity. So I'm just going to write them all as pluses right now, but obviously some of them are going to be negative. Okay, but we definitely got this. And so if we attach the signs on it, in this case, we're going to have F2 minus F1 minus gravity. And we know that this is going to have to end up equaling 0. Or, well, maybe not equaling, it's actually going to equal mass times acceleration. Right, Newton's second law. Okay, so there's that bit in the Y. So in the X, what we know is that those two horizontal components have to be equal, because this wave is not moving left and right, or this particle, I should say, is not moving left and right. So those two are just going to end up equaling each other. We'll keep that in mind, but for right now, let's just do this bit so far. Okay, now if we zoom in on this picture, we've got our two different thetas. And in fact, how about we maybe look on the left-hand side of this little strip and the right-hand side. So we do have a little thickness. So we're going to really zoom in now. So here's that chunk of the rope that we're looking at. And so there is going to be an angle that it forms with the string and the tension. So let's say this is the string coming up like that, like before. So let me give you some thetas. So we're going to have two potentially different angles. Let's call this one theta 1. And this one's going to be theta 2. And so if we look at the components of the force and all that, we're going to see that the tangent of theta 1 is going to be your vertical bit over your horizontal bit. So from this, we're going to get tangent of theta 1 equals the minus F1. That was our vertical bit. That's the one we were calling F1. Over whatever the horizontal force of this tension is. I'm going to call it F sub x. And then theta 2, similar story, except it's going to be F2 over that F sub x. But like I said before, those F sub x's we know are the same because it's not moving left and right. Okay, so we've got this relationship, but I can do even one better. Tangent. I don't know if you remember this, but the tangent of a line is actually equal to its derivative. Maybe you've never seen that. The tangent of a tangent line is actually equal to its slope. So basically what that means is I can change those into partial derivatives, since we're kind of going with a time independent view here. And so the slope, well, it's going to be the partial evaluated at the two x values. So let's say that this guy is, say, x1, and that one is x2. So I can kind of piece that together with this to get that f1 f1 over fx is going to be the negative partial derivative with respect to x at x1. I was going to put a little sub x1, or no, better. Let's do it this way. And then from the next one, we get that f2 over fx is the same deal. It's the partial, it's a positive partial though this time at x2. So if I want f1 and f2, I can just multiply those things both by fx. So here's how we're going to get that net force then. Remember that it was f2 was pointing up minus f1. There's our minus sign, right? So we're going to get, if we look at f2 minus f1 or plus f1, it's going to be fx times the partial at x2 minus the partial at x1. And we saw that those two have to balance gravity, or they give us our acceleration, our mass times acceleration. So we put that together, and we're going to get this fx times this partial business that's going to equal mass times acceleration, where mass is mu times the length, so I'll call it delta x times a.
Mu times a.
That's mu times, this is m times a,
Mm-hmm.
which then becomes mu times delta x times a.
Okay.
I apologize, it looks like a 9. Well, let me just do two more things real quick. One, I'm going to divide by the delta x. And then the second is, if we look at acceleration, acceleration is a second derivative with respect to time. So we can write fx times this partial business so that's going to be over delta x, and then that's going to equal mu times the second derivative with respect to t, because that's our acceleration. Well, I promise we're really close here. You're probably wondering what we're doing. We're trying to get an equation for velocity, for the velocity of the wave.
So I'm just thinking about this. Wouldn't the delta x and the partial derivative stuff inside the parentheses cancel?
No, because the partial derivatives, they're not going to be the same because
Okay.
we're off by a little step. Okay, delta x was the width of that little chunk of string we were looking at. And so because this wave is traveling through, it's going to have a different rate of change at both of those spots. And the difference in those two isn't exactly delta x.
Gotcha.
But maybe, and I'm going to give you a little credit here, Bradley, so just say, yes, this is totally what you were thinking, is I want you to look at this for a second and imagine what happens as delta x goes to 0. So we bring that string chunk and we make it really, really small. Do you recognize this piece right here? It looks a little bit different, but that's a derivative.
Yeah.
Change in function value over a little tiny step. So I'm sure that's exactly where you were going, Bradley.
Okay.
Yep, good. So check out what happens then. This is going to be that fx times, well, this is now a second partial because we're differentiating with respect to x, equals mu times the second partial with respect to t. So I'll divide that fx and this is where we want to go back to what we did before the break. I showed you the linear wave equation. And we saw that the linear wave equation, we had this relationship where this multiplier is 1 over v squared. So we now have that 1 over v squared is equal to mu over fx. So v then is going to be the square root of fx over mu. But what was fx? What was causing that?
Wasn't that the total amount of force in x? Like the magnitude?
So that was the magnitude, but in each direction. And what force was causing that x direction of?
Tension.
That was tension. So I'm going to rewrite this as v is equal to the square root of tension over mu. And I didn't want to use big T because that might make you think period. But this right here tells you how fast a wave is going to move on a string. So all you need to know is the tension and then the mass density.
So the tension in the string divided by the mass divided by the length gives you velocity.
Correct. So
That's fucking crazy.
so it could be tension times length divided by mass, if you wanted to think about it that way. But yeah, so the speed of a wave on a string is really only dependent upon how taut it is and how heavy it is. So I don't know if any of you guys are musical.
That makes so much sense.
But think about guitar strings, right? You change the note on a guitar string by changing the tension. And in essence, what you're doing is you're changing the velocity of the wave. Similarly, you can change the velocity by changing the density. So if it was still the same tightness, the same tension, but it was a heavier wave, the velocity is going to be less. And that should totally make sense. The heavier the string, the wire, whatever, the slower it's going to go because it requires more energy to move that more massive string. But you could increase it by increasing the tension. And the way I like to think about it, I don't know if this is quite accurate, but the greater the tension, the harder it is for that wire to move up and down anyway, right? Because if it's really taut, it doesn't want to move up and down. So the wave energy is mostly going into moving side to side. So I don't know if that's accurate, but that's what I think of when I think about waves on a string. All right, so now you can think about this, like let's say you're out rock climbing. Let me go to a picture of me. So let's say you're out rock climbing and you want to communicate with somebody down below, but it's too far for them to really hear you very well. What you can do is you can actually pluck the string. I don't know if anybody's ever done this that has gone rock climbing, if there are any of you that are rock climbers. But you can pluck that string and that pulse will go down and then the person down here will feel it. Okay. So you can, if you were to time how far it goes down, you'd be able to figure out tension versus mass density. We actually did this backwards back in my oceanographic days. So we would remember when I showed you the compressed coffee cup. What we normally would do on those is we'd have these bottles that were like hollow tubes that then were rigged so that when something hit a little catch on it, it would cause the top and bottom, it was like spring loaded, and then it would close. And then what would happen is when it closed, it would release a weight that would slide down on the cable, and then it would hit the next one, cause it to release, send the next one, and so on. And so we could get this all set up, and all we had to do to trigger it was drop a mass. So you drop a mass from the top, it would go down, hit the first one, and then you'd get this cascading event. Okay, well, one of the things we did to help confirm that A, they were closing, and B, they were pretty much at the right depth, is we would hold on to the cable. Like you didn't have to grip it, but you just kept your hand on it, and you would feel when these things closed. Because as they closed, they would shake the cable and basically send a signal along the wire, send a pulse along the wire. So we knew roughly the mass density, and we also had a good idea of what the tension would be with how much weight we were putting on it, how many bottles and all that. And so we would let it go and we would just start doing your count. Go 1, Mississippi 2, Mississippi 3. Oh, there it went. And you go, okay, so it was about 3.5 seconds. 3.5 seconds means 800 meters. Okay, cool. That's about where we wanted it, or whatever it happened to be. So it is a very useful thing in weird situations. But you can now, it's possible to time pulses by looking at this. Okay, so that's on a string, but yay, what if you don't have a string, right? What if we've got some other kind of material? Like, what if we've got a wave in water? or we've got a sound wave in air, or any of the other very many kinds of waves that aren't actually on strings. So the question is, how can we calculate their velocities? Well, let's look at this formula in terms of what tension and mass density really are kind of a measure of. Okay, so let's go back to the board. All right, so we see that it's tension over mu. So tension is really kind of the property of the string that allows for motion, or deformation, maybe even be the better word, right? It's the property that allows for the bending of it. And then mu, that's really just a measure of how massive it is. And mass, remember, that's an inertial property. So it's kind of like how hard it is to move. So the top is how easy is it for it to bend or deform, and the bottom is how hard is it to move. And in general, that's what this looks like when we talk about waves that are in fluids or other things. All right, so let's say we're in a fluid. Now tension doesn't make sense. But if we want to think about the property that describes how well it can get deformed, that's the bulk modulus. So instead of tension, the role is going to be played by the bulk modulus. So hopefully you remember modulus. It's a ratio of stress versus strain. So we're really looking at kind of force being applied versus actual change in the material. And so bulk modulus with the fluid is pressure per area, so surface area, pressure per surface area. And then the strain is actually the change in volume, right? Because like think about that styrofoam cup. There was great pressure pushing from the outside, and it caused it to shrink in volume. Okay, so the role of tension is going to be played by the bulk modulus. And then mu, remember that was a mass per length. Well, what quantity do we use for fluids to describe mass? Or even think the name for mu is mass density. So it's still the same old density. It's just now it's a density per volume. And so if we kind of follow this same idea, this V is now going to be the square root of B over rho. So this is what lets us calculate the speed of waves in fluids. And this is usually for a longitudinal wave. So let's talk sound. Sound's a great example. So if you want to know the speed of sound, what you need to know is the bulk modulus of that material that it's going through and its density. So this is how we calculate the speed of sound in air, speed of sound in water. It does travel at different speeds. I don't know if you've ever been underwater and heard sounds. It doesn't sound quite the same as what it sounds like when it's up above. But this is how we calculate it. So for example, the speed of air or speed of sound in air is right around 343 meters per second. It depends a lot on temperature and pressure and all that, as you can probably imagine, because temperature and pressure are going to change the density. It also depends on like water vapor content and the like. Like if you're in a really humid area, the speed of sound will be different. It'll be slower because the density has increased. The air density is thicker. So like where we are in Tahoe, right, or Carson or anywhere up in here, our speed of sound is a little bit faster than what it is down at sea level. And that's just because there's less material in the air. It's less dense. Anyway, so for just about any kind of situation where we've got a wave, we can actually look at it as this elastic property divided by inertial property. So in this case, bulk modulus divided by rho. All right, so questions on that? Hearing none. Okay, well then last thing we're going to talk about today, and don't get excited, it's not like this is a 5-minute conversation, but the last topic we're going to talk about is what about energy? What about the energy in a wave and the power of a wave? How much energy is actually getting transmitted as we have a wave moving? So let's just go back to good old mechanical energy ideas. And let's look at kinetic and potential in a wave as it's moving along. So we're going to have our wave doing its thing. And just like we did when we built the speed idea, let's just look at a little chunk of this wave. And let's say that it's on a string. We can adjust it to other stuff. But this will be for energy and power of a wave on a string. But you're going to see that when we get to other kind of waves that aren't on strings, like sound and all that, it'll be very similar. Okay, so let's just go with the energy argument, and let's start with kinetic energy. So kinetic energy, as you know, is good old 1/2 mv squared. So let's start with that. So in terms of the mass of that little chunk is going to be, again, mu times delta x. So it's the same kind of idea that we did before. And then the velocity, well, let me just call that, say, Vy squared. All right, because this object is moving up and down. This little chunk is moving up and down. So it's its velocity in terms of y. And that's going to change depending upon where we are in the wave. We already saw that when we kind of built our equation for the wave. But let's make this differential. So a little chunk of kinetic energy, a little dk, it's going to be equal to 1/2 mu times dx times the velocity in the y direction squared. And the velocity in the y direction, if you go back and you look at what we derived, let's go with it like it was a cosine again. And so we saw that it was minus a omega times the sine of kx minus omega t. So this literally is just what we wrote, I don't know, an hour ago when we were talking about the wave function. Okay, so let me just go ahead and, oh, I need a square on that. So let me just rewrite this so that it's nice and neat. We're gonna have 1/2 mu a squared omega squared times sine squared of kx minus omega t, and I'm going to put dx. All right, so far so good. So that's the kinetic energy in one little chunk. But I think what might be easier or better for us is how about we look at the kinetic energy over one wavelength? Because it's going to be kind of hard to necessarily say how much is in the entire wave if we don't know how many wavelengths, how long it is, and all that. So if we just get the energy per one wavelength, that way we can kind of scale it, right? So you go, oh, okay, in one wavelength, it's this many joules. So this wave right now, we've got 4 wavelengths, so it's 4 times that or whatever. Okay, so for one wavelength, what we're going to do then is we're going to integrate from 0 to lambda, this guy dk, right? Because one wavelength will be from 0 will be wherever, and lambda will be the next wavelength. Well, most of this stuff is constant. We're going to get 1/2 mu a squared omega squared. But then we need to integrate the sine squared kx minus omega t from 0 to lambda. All right, but that's easy enough. So let's go ahead and get that. If you were going to do it by hand, which I'm not, I'm using a calculator. But if you were going to do that by hand, what you would have to do is the power reduction on the sine and then, you know, all that good stuff, which is why I'm not going to do it by hand. I forgot to do this ahead of time, so I apologize. Normally I'm a little bit more prepared, but today's been one of those days. All right, so what we get oops, hold on. There we go. All right, so we end up getting sine of omega t minus lambda k times the cosine of omega t minus lambda k. And that's all over 2k. And then we're going to subtract from that a sine of t omega cosine of t omega divided by 2k plus 1/2. And so that's all going to be multiplied by the 1/2 mu a squared omega squared. And that 1/2, that's a 1/2 lambda, sorry. Okay, so now some interesting things are going to happen. So first of all, notice I've got sine times cosine. That comes from a double angle identity. It's actually half of the double angle identity. So what we're going to get from this, let me bring that other stuff out front. That first one, we're going to get 1 over 4k times the sine of 2 times omega t minus lambda k. So I'm doubling the angle and cutting in half. The next one is going to be 1 over 4k times the sine of 2 omega t. And then again, we're left with the plus lambda over 2. All right. But now here comes the little trick. So if you look at these two quantities, I want you to notice what the difference is. Right? We've got the sine of 2 omega t minus 2 lambda k versus the sine of 2 omega t. So they're off by a 2 lambda k. Well, those two, they're identical. They're actually going to be, this 2 lambda k brings us so that we're back in phase again. So from just a little bit of trig, those two numbers are the same, which means these guys cancel. So just take my word for it right now, or if you want, hit me up later, we'll chat about it. But it comes from the periodic nature of sine and the fact that k is related to lambda with the 2 pi. Yeah, no, maybe. Again, just smile and nod, I guess. So, because that wave number, it was 2 pi over lambda, which means when we multiply that out, we get 2 pi. 2 pi times 2 is 4 pi. And so you remember sine, its period is 2 pi, so that's 2 cycles, 2 wavelengths. Anyway, those things cancel. And so what we're left with then, so here's the big thing. So this is our kinetic energy in one wavelength. It's 1/4 lambda a squared omega squared times mu. Where's my lambda mu? So if you haven't had enough Greek alphabet lesson yet, here's a good chunk of them. But again, remember this is one wavelength. So that's the total amount of kinetic energy in one wavelength of the wave. But notice what affects it. The wavelength itself. If the wavelength is longer, you're going to have more energy in one wave. Duh. If mu is greater, if it's more massive, you're going to have more kinetic energy. Duh. Amplitude. If that wave is going higher up and down, we're going to have more total kinetic energy. Again, duh. The omega maybe not as clear, but omega, remember what that is. That's your angular frequency. So it is a measure of how quickly it's going up and down. So the bigger that is, yeah, again, it makes sense that that should be more kinetic energy. Okay, well, there's our kinetic energy, which means we're only halfway done. because now we have to get our potential energy. And there's going to be potential energy involved in the string, I'm sorry, because of the fact that it's simple harmonic motion. And so here's where we're not going to invent things. We're going to use what we already know. So let me just remind you that in simple harmonic motion, we know that the potential energy, it was equal to 1/2 kx squared, where k was your spring force, basically. But we can actually relate that back to omega. We saw, this was something else we saw, that the omega was such that k was equal to a mass chunk times omega squared. It was mass times omega squared. So we can put that in. Now we got our potential energy is equal to 1/2 m omega squared x squared. So if we make this differential, we're going to get that du, little differential chunk of potential energy, is equal to 1/2. Now the mass, the little mass chunk is going to be mu times delta x. So we're going to get mu omega squared x squared times dx. And so we'll do the same thing. Let's go one wavelength. Let's integrate from 0 to lambda, 1/2 mu omega squared x squared dx. Okay, but we have to change this because the x is actually a cosine now, right? We've got a cosine wave. So when we put that in, I mean, integral from 0 to lambda of the 1/2 mu omega squared. But now that x is actually an a sine, or actually, sorry, an a cosine, because our position is cosine. So we're going to get a squared cosine of kx minus omega t squared. So we're ready to integrate that thing. And I'm just going to jump to it. We get that u is equal to 1/4 lambda mu a squared omega squared. But this is also over one wavelength. And I'm sure you see it. And maybe you're thinking I did something wrong, but I'll tell you I didn't. That's kind of cool, huh? The total amount of kinetic energy in one wavelength is equal to the total amount of potential energy in one wavelength. Okay, I think that's cool. I think it's pretty amazing that we end up getting exactly the same thing when we're looking at two very different kinds of energy, right? The one is just due to the motion of the objects, and the other is stored because of the fact that it's harmonic. Well, that of course means that if we get our total energy over one wavelength, okay, so over one lambda, we end up getting 1/2 lambda mu a squared omega squared. So that's the big end result, is we now know how much energy is in one wavelength of a wave on a string. And so again, if we've got a certain number of wavelengths, you just multiply by that lambda and you've got your total energy. And of course, from energy, once we have energy, we can get power really easily. And so this is going to be the average power over 1 lambda. So hopefully you remember how you calculate power. It's just energy over time. And so the amount of time it takes to go over 1 wavelength, that is your period, right? Or the time here is going to be, we're going to look over 1 period. So we're going to have 1/2 lambda mu a squared omega squared over our period. But this right here, wavelength over period, that's just your velocity. And so what we get for our average power is 1/2 mu a squared omega squared v. So let's go ahead and put a box around that, because that's how much power is being supplied, I guess, by a mechanical wave on a string. But notice that all of this depends upon the wave itself. We need to know the angular frequency. We need to know the amplitude. We need to know wavelength and period, or velocity. We need to know the mass density, so that's the medium itself. So all of this stuff doesn't just depend on the wave, but also the material that it's in. So I think that's enough brain damage for today. I know this was really, really mathy, a lot of derivations. But what we'll start doing next is actually looking at the phenomena. We'll talk about the physics behind the waves, because right now we're just doing the math, which I know is really kind of blah, but we need it so that we can actually do the computations for the things that we see. So we'll start talking about sound. Start talking about the things that create sound, why you hear sound. We'll talk about what happens when waves come together and we get interference. I'll see if I can replicate. I don't know if I can do this, but I'm going to try to replicate something that I do in class to really show you how sound waves interfere and so on. So that's where we're going to be going, but we'll do that on Wednesday. All right. So I'm going to go ahead and stop the recording.